Hello APC Mechanics students, today we will solve the past paper FRQ 2000, exercise number 3. A pulley of radius R1 and rotational inertia I1, the pulley is massive, which means that if the pulley is accelerating, the tension T1 on the left is not equal to the tension T2 on the right. Is mounted on an axle with negligible friction. A light cord passing over the pulley has two blocks of mass M attached to either end as shown above. Assume that the cord does not slip on the pulley, so this is important, which means the rotational motion is completely converted to translational motion and vice versa. Determine the answers to parts A and B in terms of MR1, I1, and fundamental constants. So in this case, whenever we have an answer for part A and B, we should refer to the following statement. Now in part A, they're telling us to determine the tension T in the cord. Now here you can ask the following question. Is the pulley accelerating or at rest? Now if you notice carefully, we have 2m on the left and 2m on the right, so basically we are at equilibrium, which means that the forces are balanced. Then we're interested in determining the tension T in the cord. Either we can use the left cord or the right cord. So if you consider, for example, the left cord, what are the forces acting here? We have the tension up, and these two combined will exert a pull of gravity given by 2mg downward. So we can safely say in this case that we have that 2mg is equal to the tension T, and this is the reason given by balanced forces. And we're interested in determining T, so indeed T is being expressed in terms of M and fundamental constants. Then in this case we have that the tension T is given by 2mg along the cord. Now one block is now removed from the right and hung on the left. So here we're gonna do the following. We will remove one block from here and we're gonna add it on this side. When the system is released from rest, the three blocks on the left accelerate downward with an acceleration given by g/3. Determine the following. Idea number 1, the tension T3 in the section of cord supporting the three blocks on the left. And this can be determined using Newton's second law for translation. So let me say apply. Now why we thought about Newton's second law for translation? Simply because we're interested in determining a force. And we know that Newton's second law gives us access to different forces acting on the system. Now apply Newton's second law. For translation to which system? To the 3mg, because we're interested in finding this tension. Now generally speaking, we know that Newton's second law is given by F naught is given by ma. Now what are the different forces acting on the 3m block? We have the pull of gravity, we have the tension in the cord, and this is it. This should be equated by 3m multiplied by the acceleration. Remember that this is a vector equation that gives the birth to two linear equations. We're interested only along the vertical. So projection along the vertical, and remember that because the 3mg is falling down, they will consider down to be positive. Down is positive. So in this case we have 3mg minus, now they're naming the tension to be T3, so let me adjust this. Then T3 equals to 3ma. But we know that whether the pulley is massive or massless, the acceleration of the system is the same, because simply we don't have any slipping. Then the acceleration is given by g/3. Then here we can say that 3 mg minus the tension T3 is equal to 3m multiplied by g over 3, and we're interested in determining the value of T3. Now what's the type of this equation? This is a linear equation. Now we solve for T3 by isolating. Now 3 cancels with 3, so we have 3 mg minus T3 is equal to mg. Now dragging this to the right hand side and this to the left, so we have 3 mg minus mg, which is 2 mg, and reading it from right to left, we're left with T3 is equal to 2 mg. Then in this case the tension T3 is given by 2 mg. Now in idea number 2, we're interested in the tension T1 in the section of the cord supporting the single block on the right. So remember that because this is a massive pulley and we have acceleration, so here we have the tension T3 and here we have tension T1. So T3 is not equal to T1, and we expect that T3 should be greater than T1 because we should have unbalanced torques in order for the pulley to rotate in this direction. Now we will follow the same strategy and we will say apply Newton's second law to mg now, and in this case we have F naught is given by ma. Now what are the different forces acting on the mg? We have the pull of gravity plus the tension T1, pay attention that we use the same notation, equals to the mass, which is given by m. And now this is a vector equation, we need to project it, so projection along the vertical and here in this case, because the mg of the block m is accelerating upward, we will say that up is positive. So the pull of gravity would be negative plus T1 equals to ma, but we know that a is given now by g over 3. And we're interested in determining T1. Now T1 in this case would be 1 over 3 mg plus mg, which means that the tension T1 is given by 4 over 3 mg. And indeed, if you compare the factors between T1 and T3, 2 is greater than 4 over 3, which supports our previous claim. Now in idea number 3, notice that here, because these parts are labeled by ideas, which means they might be related to each other, and all answers are being expressed in terms of m and fundamental constants. Now we're interested in determining the rotational inertia I1 of the pulley, and this can be determined or accessed by applying Newton's second law for rotation. So let me say apply Newton's second law for rotation. And now here we are applying this to the pulley. Now what are the forces acting on the pulley? We have the tension T1 and we have the tension T3. Sorry, that would be T3 and that would be T1. Although here at this point T3 is pointing up, but if you're considering the pulley, T3 would be acting away from the object. Similarly here, if you consider T1, it's acting up, but we're considering the pulley, then the tension T1 is acting down. Now what other forces are acting on the pulley? We have the pull of gravity at this point, which is down, and we have the reaction at the axle itself. Let me say this is so FR. Now these two forces, they don't produce torque in any sense, because simply because their line of action passing through the axis of rotation. So here we need to specify the point that along which we're applying Newton's second law for rotation, which is basically the center of the pulley. So let me say about the center. And now what do we have? We have tau naught is equal to I1 multiplied by alpha. Now what are the different forces? We have the torque by gravity plus the torque at the axle plus the torque produced by the tension T1 plus or let me say the torque produced by the tension T3 minus the torque produced by the tension T1 is equal to I1 multiplied by alpha. And these two, they produce no torque, so that would be 0 plus 0. And notice that the tension T3 is producing torque tangentially, then the torque would be plus T3 multiplied by R1. And now what about T1? It's producing torque in the opposite direction, so that would be minus T1 multiplied by R1. Then here we have T3 multiplied by R1 minus T1 multiplied by R1 is equal to I1, but we know that in this case alpha is given by A divided by R. Because the type of motion is rolling without slipping, then any angular variable of motion can be related to any translational variable of motion. And we know that A is given by G over 3, so that would be 1 over R multiplied by G over 3. Or let me represent it like that, G over 3R. So that would be, so let me say A over R, and we're interested in determining I1. Then I1 in this case would be given by T3 multiplied by R1 minus T1 multiplied by R1 divided by A over R1 as well. And that would be T3 R1 square minus T1 R1 square divided by A. Sorry, that would be alpha. Or no, it's A because we have replaced it by A over R1. Now T3 is given by 2 mg and T1 is given by 4 over 3 mg. So that would be now T3 is 2 mg R1 square minus 4 over 3 mg R1 square divided by A is given by G over 3. Now here G with G with G, that would cancel, 3 it goes up, that would be 3 into 2 R1 square minus 4 over 3 R1 square. So we can factor also out R1 square, that would be 3 R1 square into 2 minus 4 over 3. And here if we do the common denominator, that would be times 3 over 3, that would be 6 over 3, 3 with 3 would cancel, and we're left with 2. So that would be equal to, sorry, here also we can factor out m. So let me do it properly. Then that would be 2m R1 square. Then the value of the rotational inertia I1 is given by 2m R1 square. Now why I knew that I'm forgetting a mass, because the rotational inertia should be proportional to mass and distance square. So this is it for idea number 3. Now in part C, they're telling us the blocks are now removed and the cord is tied into a loop, which is passed around the original pulley and the second pulley of radius 2r1 and rotational inertia 16i1. The axis of the original pulley is attached to a motor that rotates at an angular speed omega 1, which in turn causes the larger pulley to rotate. The loop does not slip on the pulleys. Determine the following in terms of I1, R1 and omega 1. Now here the two pulleys are connected by this cord, and because we don't have any type of slipping, They both have the same linear speed, which is given by v, however omega is different. So they're telling us in idea number 1 the angular speed to determine the angular speed omega 2 of the larger pulley. So here we can say the two loops or the two pulleys have the same linear speed, which means v1 is equal to v2. What does v1 represent? It's the linear speed along the rim of the pulley, and v2 represents the linear speed at the rim of pulley 2. So that would be r1 omega 1 is equal to r2 omega 2, and we're interested in determining omega 2. Then in this case, now here what do we have? We need to express in terms of I1, R1 and omega 1. Now R2 is given by the double of R1. So let me here write it as the double of R1 multiplied by omega 2. R1 with R1 cancel, then omega 2 would be given by the half of omega 1. Now the angular momentum L2 of the larger pulley, we know that for a rigid body the angular momentum is given by I multiplied by omega. If this carries the subscript 2, that would be 2, that would be 2. Now what about I2? I2 is given by 16 I1. And omega 2 is given by omega 1 over 2, that would be 8 I1 omega 1. Then the angular momentum L2 is given by 8 I1 omega 1. And indeed, again, our answer is being expressed in terms of I1, R1 and omega 1. Now they're asking us to calculate the total kinetic energy of the system, and here the kinetic energy is purely rotation. Then K would be K1 plus K2, and we know that for pure rotational motion the kinetic energy is given by half I omega square carrying the subscript 1 plus half I2 omega 2 square. Now we're gonna leave these as 1, and that would be the moment of inertia I2 is given by 16 I1, and omega 2 is given by omega 1 over 2. That would be half I1 omega 1 square plus, now here you would have over 4, 16 over 4, that would be 4, 4 over 2, that would be 2. So 2 plus half, that would be 5 over 2. Then in this case the total kinetic energy of our system is given by 5 over 2 I1 omega 1 square. Then that's it for me in this video, guys. See you soon in a new one.